In this section, we are looking at types of reactions. You will be able to identify a chemical reaction as a combination, decomposition, single replacement, double replacement, or combustion reactions. A great number of chemical reactions occur in nature, in biological systems, and in the laboratory. However, there are some general patterns that help us classify these reactions into 5 general types. We've got combination, decomp, single replacement, double replacement, and combustion. Let's start with the combination reaction. Combination is when we have 2 or more reactants to combine and form a single product. Here's the general format. A plus B gives me AB. Here's an example. Sulfur plus oxygen gives me sulfur dioxide. Here are some more examples. I can have magnesium plus oxygen to give me magnesium oxide. Notice that this is balanced. Magnesium, I need 2 magnesiums on the left and 2 magnesiums on the right. Oxygen, when it's by itself, is always diatomic, so there's 2 O's on the left and 2 O's on the right. This is my format A plus B to give me AB. Notice that my A is magnesium and the A stays with magnesium. The B is oxygen and B is oxygen. Don't think that because this is O2 you would carry your O2 to the product. We know that magnesium forms an ion that's a positive 2 ion, and oxygen forms a negative 2 ion. Therefore, the 2 and the 2 give me a neutral compound. I do not need to put a 2 here and a 2 there. They would reduce to 1 and 1. That's why I need the 2 in front of that magnesium oxide. The second example we have is nitrogen plus hydrogen to give me NH3 or ammonia. Again, nitrogen and hydrogen, when they are by themselves, are also diatomic, but when we're together in a compound, we have NH3, then we need to balance it. We also, for a combination reaction, can have 2 or more simple compounds, not just loner elements like magnesium, nitrogen, oxygen, hydrogen. They don't have to be just elements, but they can be simple compounds that combine to form one product. So I still have A, I still have B, so I have one thing plus another thing to give me one product. That's the key. One product for a combination reaction. This just shows us at the particulate level. The magnesium, we can see magnesium atoms here, plus oxygen atoms. We can see the oxygen is diatomic, and then they react to form. Bonds are broken, and new bonds are formed. Magnesium oxide, 1 magnesium with 1 oxygen, 1 magnesium with 1 oxygen, and it forms a lattice. Our second type of reaction is a decomposition reaction. That's when one reactant splits into 2 or more simpler substances. Think of something decomposing or breaking down. So I'm starting with one reactant on the left side of the arrow, and we're breaking it down into what it's made of. In this case, I have mercury oxide breaking down into mercury and oxygen. Remember, oxygen by itself is diatomic. Here I have potassium chlorate breaking down into potassium chloride and oxygen. It's okay that this is a compound. We are taking one reactant and breaking it down into simpler substances. Here's a picture at the molecular level showing us the mercury 2 oxide breaking down into mercury and oxygen. Single replacement reactions is when an uncombined element replaces an element in a compound. I like to call this the third wheel. The third wheel, we have a loner element and I have a compound. We'll call it BC. If I have a compound, remember the first one listed is my metal and the second one is a nonmetal. Now let's pretend that A is a metal. Let's say I have zinc or iron. It wants to kick out the metal that's in the compound. It wants to do a date swap. So A is going to kick out B, leaving poor B by itself. In this case, zinc is going to say, see you later, hydrogen, you can be by yourself. And zinc will take hydrogen's spot to make zinc chloride. Iron is going to kick out copper, so copper will be by itself, leaving iron with the SO4, so iron sulfate. At the atomic level, we can see that we have zinc plus hydrochloric acid, HCl, and it's going to rearrange these bonds. The zinc is going to kick out the H, leaving hydrogen by itself. And then zinc, since it took H's spot, will be left with zinc chloride. The next step is the double replacement reaction. And in this case, we have 2 elements in the reactants exchanging places. The A and the C are both metals. We know that B and D are nonmetals. These two metals are going to do a date swap. It's a double date swap. So A will then be paired with D, since it's taken C's spot, so A with D. And then C is going to pair with B over here. Make sure that the metal is listed first. In this case, I have silver nitrate plus sodium chloride. Silver and sodium are both metals, so they're just going to swap spots. I would be left with sodium nitrate and silver chloride. It doesn't matter which order you have them in. In the second example, I have sodium hydroxide plus HCl, so the Na and the H are going to switch spots, leaving me with HOH, which is H2O, and NaCl. Here's an example at the molecular level showing the sodium sulfate plus barium chloride. Breaking bonds, rearranging bonds, the sodium and the barium are switching spots, so I'm left with barium sulfate and sodium chloride. This is our last type of reaction. It's called a combustion reaction. It's when we have a carbon-containing compound burning in oxygen from the air to produce carbon dioxide and water and heat. So notice I have a carbon-containing compound plus oxygen to give me CO2, H2O, and heat. Here's an example of butane, which is an alkane that has 4 carbon atoms and 10 hydrogen atoms, so C4H10. It's a carbon-containing compound. It's used as fuel for camp stoves. So I have my hydrocarbon plus oxygen to give me CO2, H2O, and heat. Here's a summary of the different reaction types. This shows us on the left the general format. So a combination is A plus B to give us AB. And then over here we have examples. Calcium plus chlorine to give us calcium chloride. Here's another example of diatomic. In fact, all of the diatomics that you need to remember spell out Brinkelhoff. You'll want to write these down. Bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. When they are by themselves, are always diatomic. You will find them paired up with one another because when they are by themselves, they're very unstable as a single element. It wants to be paired with itself. So here I have calcium plus chlorine to give me calcium chloride. A decomposition reaction. Here's an example where I have iron 3 sulfide breaking down into iron and sulfur. A single replacement, I've got loner copper plus silver nitrate. So copper is going to kick out the silver, leaving me with copper nitrate and silver by itself. Notice silver by itself is just Ag. Iron by itself is just Fe. Sulfur by itself is just S because none of those are in Brinkelhoff. Brinkelhoff is always diatomic, so we need 2 of them. Here's a double replacement reaction. I've got barium chloride and potassium sulfate. So the barium and the potassium are going to swap spots, leaving us with barium sulfate and potassium chloride. And here's another combustion reaction. It's the same one we saw with methane. Let's do a sample problem. Why don't you pause the video here and identify each reaction. Pause the video. Hopefully you got combination reaction, single replacement, double replacement, and a decomposition reaction. How about this? Write the reactants and products for the complete combustion of butane and balance the equation. Butane's formula is C4H10. Hopefully you have the general format as C4H10 plus oxygen to give me CO2, H2O, and energy. Now we need to balance it. Here I wrote down our atom count, and on the left I have 4 carbons, on the right I have 1. So I need to put a 4 in front of my carbon-containing compound on the right. That'll give me 4 carbons, and that'll give me 8 O's plus 1 O is 9 O's. I have 10 H's on the left, so to get to 10 from 2 I need to multiply by 5. That'll give me 10 H's. Now let's recount our oxygens. 8 oxygens in the CO2 plus 5 oxygens in the water is 13. Now how do I get to 13 from 2? 2 times 6 is 12. 2 times 7 is 14. So between 6 and 7, I would say 6.5 times 2 would get me 13. Except for remember, I can't have a decimal point as a coefficient, so I need to double everything. There was 1 right here, so I'm going to put a 2. 6.5 doubled is 13. 4 doubled would be 8, and 5 doubled would be 10, giving us this balanced equation. Take a minute to look over the learning goal and make sure that you feel comfortable identifying these chemical reactions.